Alrighty, in this video we're learning about rotations about the origin. Now I want to start off with a really simple example. We've got this point here, 3, 5, and it sort of looks like this, 3 there, 5 there. So it's sitting right up there. Now if I draw the line out to this point, it's going to look like that. And then we want to rotate it by 180 degrees clockwise. That should say anti-clockwise, my bad. And that's going to look like this. So 180 degrees, and it should point out the same length. So what we should end up is right here, which is -3, -5. Now, really importantly, we've got some notation here. So 3, 5, we're going to be calling xy. This new point, we're going to be calling x dash and y dash, and that's sort of our point after rotation. So we've done that example visually, but we can do it with matrices, and we use this matrix here. So we define this matrix A, and it's going to be cos theta. It's going to be minus sine theta up the top right, and then sine theta positive down the bottom left. And then we know here theta is 180 degrees. So you just have a look at your unit circle, and you figure out cos of 180 is -1, and the sine value is 0. So our rotation matrix here, all the coses will become -1, and all the sines will become 0. This is our matrix A. Now if I want to rotate a point like 3, 5, I need to take my matrix A and times it by the point 3, 5. Let's see what happens here. So that should give us our new point. Rho times col. So we're going to end up with -1 times 3 plus 0 times 5. And then we're going to get rid of that row there. And instead, we're going to do this row. 0 minus 1 times col. You get -5. So, oh my goodness, this point here is the point x, y. Just like what we found there. So we know we're correct. Let's do a similar example here. We're going to take the same starting point here, 3, 5, and we're going to rotate it by 90 degrees. So what we'll be looking for is pretty much a right angle here. And then this point here, we're going to call x dash, y dash. So we'll figure out what that is. Our rotation matrix again has to be cos of theta minus sine of theta. And in this case, theta will be 90 degrees, and that should say anti-clockwise, because you always rotate anti-clockwise. So let's see what we're going to get. If we map out what 90 degrees is, then cos is 0 and sine is 1. So we'll use those values there. 0, 0, minus 1, 1 is going to be our rotation matrix A. So to get our new rotation, we need to go -1, 1, 0, and we need to times it by our original point, 3, 5. And what are we going to get? You can get row times column, so you're going to get -5, and then 3 for the next one, which should be our point, -5, 3. And if you sort of look at the coordinates there, yes, we are at -5, and we're at 3, and you can see that's a beautiful right angle anti-clockwise. So that original point we call x, y, and that new point we call x dash, y dash. That's after rotation. Now, the bit where it gets really interesting is when you're no longer doing rotations by predictable values, you're just doing them by something random here. Now, 2 pi over 3 is about 120 degrees if you prefer that, but we're going to be using the radian mode here. So our A matrix needs to be cos of theta minus sine of theta, and the value is 2 pi over 3, which is on your unit circle. There it is. So cos is -1/2, and sine is √3 over 2. So we use those. And that's going to be, I think sine was minus √3 over 2, wasn't it? No, it's positive √3 over 2. So that's positive √3 over 2, and that sine goes negative. So that is our rotation matrix by essentially 120 degrees. If you were to times that by a point, you would get the new point. Last thing we've got to do here is to find the nature of the transformation with those equations. So essentially, we can write these equations 3x take 4y over 5. If you think about writing it like this, 3 over 5 is the coefficient of x, and minus 4 over 5 is the coefficient of y there. 4 over 5 is the coefficient of x, and 3 over 5 is y. And then you would want to be like timesing that by xy. You can imagine if you times these, you would get the equations that are sort of up here. So this is the matrix that we call A, and we have to figure out it should match the form cos of theta minus sine of theta. Now it's not guaranteed this is going to be a rotation, this transformation, but it turns out that it is because it has this form. And the really key thing is that the determinant of A should be 1. So does determinant of A equal 1? That will help us decide whether it's a rotation. To get our determinant of A, that's 3/5 times 3/5, so it's the diagonals. Take the other diagonals, minus 4/5 times 4/5, and we get another negative sign there. That gives us 9/25 plus 16/25. So the determinant of A is definitely 1. So we know we have a rotation. Now we just have to figure out what it is. So essentially you're going to have this situation where cos of theta equals 3/5. And you can essentially just do theta equals inverse cos of that. And we'll see what we get. So let's go and make sure we're in radians just to be fancy. We're going to do inverse cos of 3/5. We're going to get 0.927 radians. Okay, now really importantly, you could get this as well by doing inverse sine of 4/5, and we'll just check that we get the same thing. Indeed we do. So whatever way you slice it, what we have here is an anti-clockwise rotation of 0.927 radians about the origin. That is what this transformation is describing.